Good evening. Good evening and welcome to the first SLAC public lecture of 2012. Before we begin, I'm instructed to just give you instructions on how to get out of here in case there's an emergency. So I'll do the flight attendant thing, 2 doors in the back and 2 doors here. It'll be done. Okay. This is 2012 is the 50th anniversary of SLAC, and there'll be numerous 50th anniversary celebrations during the year, many of which are open to the public. Please scan our For Visitors website during the year to be apprised of those events. But one of those events is a kind of theme in the public lectures running through this year. There'll be public lectures every other month, typically the fourth Tuesday night of the month as we go forward, every other month. And we're going to highlight the theme areas for SLAC in the next 50 years. These include, of course, nanotechnology, high energy physics. You'll see astrophysics. You'll see many of these topics as you come through the year. The first one is energy. And actually, we're very lucky to give this talk about things that are going on here in energy science. Professor Mike McGehee from the Material Science and Engineering Department at Stanford. Mike got his start actually in materials physics. He studied at UC Santa Barbara with the Nobel Prize winner Alan Heeger. He has been a professor at Stanford. He's now also a senior fellow of the Precourt Institute for Energy Sciences at Stanford. And he's taken the knowledge that he got in terms of solid-state physics and unusual materials to make some real strides in how you make solar cells that can transform energy in a very effective way. And so that's what he'll talk about today. So please welcome Mike McGehee.
Thanking SLAC for giving me this opportunity to speak tonight, and I want to thank you all for coming. I got a lot worried this morning when I found out that I would be competing with Barack Obama for an audience. He's well known for his speaking skills. Anyway, I'm very pleased that so many people have come, and maybe more will be rushing in now that the President's State of the Union address is over. Well, tonight I'll be talking about my favorite topic, printing solar cells for greener energy. And I'm going to be answering these questions here that you see. I'm going to be telling you what solar cells are, how they're used. I'm going to address the key question of when solar cells will be able to compete with coal-fired power points on a cost basis. I'll tell you a little bit about how conventional solar cells are made and how they work, how efficient they can be. And then I'm going to spend the second half of my talk on a newer technology, and I'm going to show you how you can print solar cells on roll-to-roll coating machines like the one that you see here. And I want to thank the SLAC art team for producing this wonderful poster and cover slide. So first, what is a solar cell? In its simplest terms, a solar cell has a slab of semiconductor in between 2 electrodes. And those electrodes are metals, and they can carry the current off. And sunlight gets absorbed by the semiconductor, and that energy is temporarily stored, and I'll say more about that later. And negative charge goes to one of those electrodes, and positive charge goes to the other. And it builds up both a voltage and a current. And you could run a light bulb off of that, or you could run the current into a battery, and you could store that electrical power and use it later on, or use that electricity to do whatever you would like to do. There are other ways you can harvest solar energy, and you can do something like heat up a fluid and vaporize it and run a turbine. But that's not what I'm going to talk about tonight. I'm going to talk about what are called photovoltaic cells, and they absorb sunlight and generate electricity. So how are they used and where are they used? Well, they're very valuable in places where there is no electrical grid. I took this picture when I was trekking in Nepal, and at this hut here, this is their only source of power, and they put their solar module out every day, and each one of those circles is a silicon solar cell, and they charge up a car battery, and then at night they're able to run a couple of light bulbs so that they can read and do things in the evening. There are other places where it's very helpful. When I was in Nicaragua, I took this picture, and this is a solar panel on the side of a Land Rover, and these people like to go way off the grid, and this gives them some electrical power. And then this next application is about as far off the grid as you can possibly be. This is the International Space Station, and these are solar panels. This is a crucial source of power out in space. Satellites depend on solar panels in order to get electricity. And this market opened up a long time ago, back when solar cells were still extremely expensive, because this application is so important that cost wasn't very much of an object. But as important as these applications are, what gets me really excited is using solar cells to try to generate a large fraction of our power so that we can stop burning coal and fossil fuels, which puts carbon dioxide into the atmosphere and causes other forms of pollution as well. And here is a map of the United States, and if you look on that, there's a red square there. And if we were to cover that red square with solar cells at 15% efficiency, which we already have available, we could meet the entire country's electricity needs. And some people look at that and they think that I'm showing how impossible it would be, but that's not how I see it. I don't see that as an insurmountable challenge to cover that area. And to put it into perspective, we've already covered that area in this country with asphalt for roads and parking lots. So this is something that can definitely be done. So why do I think solar cells, why are they likely to provide a significant fraction of our power? Well, we have a serious energy problem, and I'm not going to dwell on that tonight. But the world's going to need about 30 terawatts of power by the year 2050. And I won't talk about other ways to meeting it, but it's a hard problem. But the sun constantly puts down 120,000 terawatts of power. So the energy we need is definitely coming to us for free from the sun. Solar cells are safe, they're quiet, they have very few non-desirable environmental impacts. The main impacts would be in the actual manufacturing of the panels. When they're deployed, they hardly cause any problems at all. Maybe small problems when you start covering the desert, but compared to the other options we have, they have the least environmental impacts. And solar cells generate electricity. A lot of people, it's funny that interest in solar goes up when gas is expensive and it comes down when gas is cheap. But we use gas to run automobiles. We don't, right now, use a lot of electricity. Solar cells compete more with coal-fired power plants, and burning coal is one of our worst ways of putting carbon dioxide into the atmosphere. Coal is pure carbon, and when you oxidize it, you get CiO2. You don't get much water. And so it's one of our worst sources of CO2, and replacing it with solar is relatively easy. In contrast, getting away from gasoline in automobiles is tough, because gasoline is an amazingly good way of storing energy. So I see this as low-hanging fruit to reduce carbon emissions. And finally, Well, there is a bad thing about solar. You know, you don't get the power whenever you want it. You only get it when the sun is shining. We do get it exactly when we need it the most. We get it during the day, which is when people are using more power. And especially in a place like California, the time when we really need more power, the time when the utility companies are begging for it, is on a hot day in the summer when people are running their air conditioners. And that is exactly when we know the solar cells will be generating the most electricity. So the production of the electricity is matched with when people need it, and that greatly mitigates the intermittency problem. So here are the three big photovoltaic markets. People use them at home on their roof, and one important thing to realize is that you don't have to use the electricity when it's generated. If you're producing more than you need, you can just run your meter backwards, put it into the grid, let someone else use it, and then you're allowed to take electricity back later on. And so the grid becomes a very good, effective way of storing that energy and making sure it gets used. Another place you can put it is on large commercial buildings, like a Costco building or a Walmart would be a perfect example. An advantage of going here is that the installation ends up being cheaper. Over here, it's a custom job, and you have to get a permit, and the permit cost can be a good fraction of the overall project. But when you do a big installation, those permitting costs get spread out, so it's cheaper on this scale. And then it's even cheaper when you do utility scale power plants. And of course, another advantage of the residential is you generate the power right where you need it, whereas when you do it down here, you still have to have the grid to get the electricity where people are going to use it. So why aren't we getting all of our electricity from solar? Well, it's still relatively expensive, but that has been changing dramatically over the last 3 years. And in solar, if you're not getting your information updated in the last year, then you're not up to speed on where things are. Because in 2008, it cost about $6 per watt to install solar panels. That means that a watt that's the power you would get at noon under direct sunlight. And so for that 1 watt capacity, you had to pay $6. But over the last 3 years, that has come down to less than $3 per watt. It's come in half. And then if you look at the breakdown here, the blue part, that's the module itself, and then the rest is profit and installing it and getting a permit and putting in an inverter to switch it from DC electricity to AC. And so you see now it's about half and half to put it in and half to make the modules that I will be talking about. Now we can address when will these solar cells compete with coal-fired power plants. So this is a complicated plot, but it's a really good one, and let me walk you through it. Each one of these curved lines tells you the price in dollars per watt that the solar cells would need to be to compete with coal. And so if we look around here, Italy falls between $6 and $8 per watt, so you need to be at about $6.50 per watt in Italy. Now in other places, the costs are different, and that's because different places have different costs for electricity, and they have different amounts of sunlight. So we look along here, and we see that in places like Denmark and the Netherlands, electricity is more than 30 cents per kilowatt hour. They don't have great natural resources to generate it, and so it's very expensive up there. In contrast, in China or India, it costs less than 10 cents per kilowatt hour. And that's because they're burning coal, and they don't have the environmental regulations that we have in the United States or that Europe has. And so you have to keep in mind that wide variation in how much electricity costs. And then in California, it varies. The average is around 15 cents per kilowatt hour, but in many places in California, the amount you pay depends on how much you use. And if you use a lot, they ratchet you up into a higher system, to a higher rate. So people who are in Tier 4, they pay over 30 cents per kilowatt hour, and Tier 5 users are almost at 40 cents per kilowatt hour. Now on the x-axis, we have how much sunshine you can get, or how much power you generate per kilowatt that you install. And so what this is showing is that in sunny places like California and India, you get 3 or 4 times as much sunlight as you would get in Northern Europe or in a place like Seattle or England. And so of course it makes more sense to go with solar in the places that have more sunshine. So now we can install systems at about $3 per watt. And so everything in green, those are places where we're now at grid parity. That means that we can generate power with solar and compete with what it costs to get it off of the grid. And then below that, those are places where it would not be competitive and it would not make sense for people to put it on its rooftops. And I actually had to update this plot for this talk because I used to have a 3-year-old version, and the green region was just a small portion up in here. So things are changing rapidly, and as the costs come down, more and more markets are going to open up, and you're going to see solar being used much more widely. Here you can see the growth of the industry, and it's growing at a remarkable rate. It's grown every year for decades. It averages about 40% growth every year, and it's just taking off. And to put some of this into perspective, last year, 2010, we don't have the numbers for 2011, 2010 there were about 24,000 megawatts installed, and a typical coal-fired power plant or a nuclear power plant would be about 1,000 megawatts. So the equivalent of 24 power plants were installed around the world with solar. And that's still, relatively small. It's not that considerable compared to coal and natural gas and nuclear. But with 40% growth, you're going to see that really take off over the next decade. And in about 10 years, solar could be meeting all of the new electrical needs around the world. Now, how far will this go? So I've said before, in 2050, we're going to need about 30 terawatts. And I think a very realistic goal is to get 20% of that from solar. I personally hope we can do a lot better than that. But I do recognize that when you try to get all of your power from solar, you also have to have extremely good energy storage that is at very low cost. And that would be a topic for a whole other evening. And we'll need to see advances along those fronts. But at 20%, you're getting the power you need during the day from solar, and then at night you're still relying on things like nuclear or natural gas. So I think 20% is very realistic, and 20% of 30 terawatts would be 6 terawatts. But when I say a watt of solar, you have to keep in mind that I mean at noon. And when I say we need 30 terawatts, I mean averaged over the day. So we would need about 5 watts of solar to average 1 watt throughout the day, including the nighttime. So we would need about 30 terawatts of solar panels to give the world 20% of its power. And let's say that they last for 30 years, then at steady state, we would need to make about 1 terawatt every year. And in 2010, we did 0.024 terawatts. So we're still in the very, very early stages. And later, I'm going to show you that silicon solar has 86% of the market, And a lot of people think that the race has been won and it's all over. And I want to tell you that the race has just started. It's still the early days for solar, and there's going to be enormous growth for decades. And it will be interesting to see who captures this terawatt market that will be there in about 15 or 20 years. Okay, now let me turn to the science and tell you a little bit more about how these solar cells work. The heart of all solar cells is a semiconductor. And what is special about a semiconductor is that they have energy bands in them, one called a valence band and the other called a conduction band. And in between that, there is a band gap where there are no energy states. So down here in the valence band, the energy levels are so close to each other that on a plot like this, you can't even see them. It just looks like a continuum of energy states. And normally, pretty much all of them are filled with electrons. Then there's this gap where there are no energy states. And then there's the conduction band where there are also lots of energy states, but normally there are hardly any electrons at all. Electrons try to settle down into the lowest energy state they can get into. It's sort of like water will try to get down as low as it can. Here, electrons will try to get as low down there as they possibly can. When you shine light on a semiconductor, you can excite the electrons out of the valence band up into the conduction band. And then the energy between here is basically stored until that electron falls back down. And so later I'm going to show you how if we can pull that electron off to one electrode and we can pull this positive charge, which we often call a hole, off to the other electrode, then we can use that electrical power to do something, charge up a battery or run some kind of machine or a light bulb. So now one of the most interesting questions is, how big should that energy gap be? We have lots of semiconductors, and we can choose the right one to get the gap that we would like, but we need to know what should that energy gap be. And to answer that question, I want to use an analogy here. If we wanted to capture hydropower, we want to capture rainfall and let the water run through a turbine and generate electricity, we'd have to decide where do we want to put our reservoir. On the one hand, if we put it up at the top of the mountain, then the water can fall down over the maximum possible height, and we'll be able to get a lot of energy out of that water. The only problem is we can't collect any water at the top of the peak. There's no land to capture that water and funnel it in. So we think, well, then we want to put the reservoir down way low because then we can capture all the water. But if it's down low, we don't have much energy stored, and so we can't do as well either. So we're going to want to put the reservoir somewhere in between where we can get a lot of energy from the water and still capture a lot of the water. And that's how it is in a solar cell as well. We need to get the right band gap because when light comes in, it'll excite electrons from the valence band up into the conduction band, but they will very rapidly fall to the bottom of the conduction band. We call that thermalization. And the energy we can get out will be the band gap energy here. And so we want that gap to be high so that we can ultimately generate a large voltage. But if we get greedy and we try to make the gap too large, what will happen is most of the photons from sunlight will not have enough energy and they will not be able to get the electron across the gap. If the energy is too low, the photons will just go right through the semiconductor. And so we know the solar spectrum, we know how many photons there are with all the different energies, and we can run calculations and we can figure out how much efficiency you can get from the solar cell as a function of the band gap energy. And it turns out the best we can do is about 31% efficiency, and the band gap for that is about 1.4 electron volts. So unfortunately, we can't harvest all of the solar power. We can only get about 31% of it to make electricity. Okay, so now how do we make these solar cells? If you have solar panels on your roof, the odds are they are made out of silicon. About 86% of all the solar cells that are sold today are made out of the semiconductor silicon. And it basically comes from sand or rock, SiO2. There are ways to pull the silicon out of that, and you can get a crude form of silicon, and then you can melt that, and you first purify it and melt it, and then you can grow very high quality crystals, and then you can saw them and slice them and get a wafer like the one that I'm holding here in my hands. And you can put some boron and phosphorus in there that'll help the electrons to go to one side and the holes to go to the other. You finally put electrodes on top. If you look at it here, these silver lines, those are electrodes that help pull the current out to the side. And finally, you can connect a bunch of these in a panel and put some glass over it to protect it, and then finally install those on a rooftop. And that's the basic flow of how most of the conventional solar cells are made. Now, a lot of people believe that this will always be the best technology. They think that the industry has such a big lead and that they've achieved economies of scale and that no one will ever beat this. But many other people, and about 225 startup companies here in Silicon Valley, believe that they can find a better way to do this. This whole wafer is silicon, and it's a very pure material. It's relatively expensive, and a lot of people think we really don't need the whole thing to be high quality semiconductor. They think that we should switch to what's called a thin film solar cell, or some people call them second generation solar cells. And here the idea is that we're just going to put a thin film of semiconductor on a cheap substrate, which could be glass, or it could be a thin film of metal, or maybe a thin film of plastic. You know, we all know how cheap plastic can be. Or even some people are starting to talk about putting it on paper, which is one of the cheapest thin materials you can possibly think of. And now you don't use as much expensive material, and if you use a metal foil or you use plastic or you use paper, it can be flexible. And so you can imagine just rolling these solar cells out on a roof, and not only is your solar cell cheaper, but it's cheaper to install the solar cell as well. And so those are the reasons why people are really excited about these thin film solar cells. The industry leader right now, the material that is giving the best product is cadmium telluride. And there's a company here in the United States called First Solar that makes it. And it only takes them about 2.5 hours to make modules that have an 11% efficiency. I should have told you that the silicon ones, their modules are typically around 16%. So these are not quite as efficient, but they're definitely cheaper. And here you can see the remarkable growth of the manufacturing. They did nothing in 2004, 25 megawatts in 2005, and then it's just shot up. And now they're doing nearly 3,000 megawatts per year. Their costs are way down. Earlier I told you the average costs of the overall industry, but with this technology, even over a year ago, they were already down to just 77 cents per watt for these thin film solar cells. Another important thing people ask, do the solar cells generate as much energy as it takes to make them? And the answer is definitely yes. There's crazy myths out there that they don't. It only takes 8/10 of a year to generate as much power as it took to make these, and they last for well over 20 years. So they generate way more energy than you need to make them. And so this kind of brings you up to speed. These are two of the best technologies that are out there already. These are things you can buy. And now I'll turn to printing solar cells. So we want to drive these costs down even more. We want to get to 50 cents per watt, and we want the efficiency up over 20%. The Department of Energy has a goal of being able to install the whole system for $1 per watt, and we'll put half of that for the module and half of it for the installation. And if you can do that, you compete with coal-fired power plants everywhere. You hit grid parity in all places. And so here's the printing. There's a startup company nearby called NanoSolar, and they have come up with a way to print another thin film semiconductor called SIGS, which stands for copper, indium, gallium selenide. And I can't tell you exactly what's in those particles, but it contains those elements. And they print that down in a roll-to-roll coating machine. It's not completely unlike a newspaper printing press. And they print those particles down, and then they heat them at about 400 to 500 degrees, and those particles fuse together, and they end up with a high-quality thin film of the semiconductor, and they are able to make solar cells with 17% efficiency. And that's their record in their research and development branch of the company, and the manufacturing branch is already putting out modules with 11% efficiency. And here you can see a picture of the roll. This is a massive roll of aluminum foil, and it goes into the roll-to-roll coater where they're able to print the copper, indium, gallium selenide. And I only have 50 minutes to talk tonight, and I can't show you everything I'd like to show you. So I encourage you to go to their website, and you can see videos of the solar cells being made, and you can even see the robots cutting the stuff up and then putting them into modules and packaging it into glass. Okay, so these are the conventional materials. The ones that gets the most attention are silicon, cadmium telluride, and SIGs. And you can see here the record efficiency, the typical module efficiencies that the companies can make, and sort of where the costs are right now. And a lot of people, believe these are the front runners. But at the university and here at the National Lab, we're given the challenge of thinking further out, thinking 10 years, 15, 20, 25 years out, and thinking about what might be even better than these. And it's our job to think of what problems these technologies might encounter down the road. And so some of those problems might be that, well, cadmium is toxic, and we would love to get away from that if we can. And tellurium and indium are not abundant elements. And if you run some simple calculations, you can look at the US Geological Survey, and you'll find out that in all of our known supplies, we don't have enough tellurium or enough indium to make a terawatt of cadmium telluride solar cells every year, or SIG solar cells every year. And the people who work for those companies will tell you that if we look hard, we'll go out and find more of those elements, but that remains to be seen. And so we are working on developing other materials that don't rely on any toxic elements or elements that we don't have in abundance. And that brings me to the research that we do in my lab at Stanford and up here at SLAC. We work with organic semiconductors. And by organic, what I mean is carbon-based compounds. We did not raise these on a farm that does not use fertilizers or pesticides. They were synthesized in the lab, but they're carbon compounds. And I'm going to be talking later about donor materials, and they're good at transporting the positive charge, or the holes, and acceptor materials, and they're good at transporting the electrons. And since this is a short talk tonight, I won't get too much into the chemistry, so don't worry about the complicated chemical structures of some of these molecules. Okay, so why are these organic materials exciting? Well, first, I've already told you these are abundant, low-cost materials. Here you see the chemical structure of copper phthalocyanine, and it's a molecule that's already used in blue car paint. So already, I think something like 100,000 tons of this stuff are made every year. So it's available and it can be cheap, but even more importantly, we can spray it really fast, and we can put it on plastic substrates. We do not need to heat this to 400 degrees, and so we can use plastic, and that means that our solar cells can be very lightweight and very flexible. This is a module that was made by a startup company in Massachusetts called Canarca, and you see that it is totally flexible, and if you want to come handle it later, you'll see that it's also extremely lightweight. And so you can imagine rolling this stuff out on the roof and nailing it down, and that would really bring down the installation costs, and it would allow you to install it on old homes that are not able to support the weight of heavier modules that might be packaged in glass. And you can imagine doing some even more exciting things. This is an emergency space blanket that I picked up at REI. A lot of people like to carry these when they go into the wilderness, and if they unexpectedly have to spend the night, they wrap themselves in this blanket and it keeps them warm. If you unfold this, it covers 3 square meters. If we put 10% efficient solar cells on this thing, it would generate 300 watts of electrical power, which would run 3 laptop computers. So if you got lost in the wilderness and you needed to keep your flashlight going, keep your GPS unit going, keep your transponder going to tell people where you are, this would make absolutely sure that your batteries didn't go bad. And this is actually way more than you need. I could make something about the 5th of this size, and it would fit like inside of a canister that would be smaller than a pen. And when you needed it, you could fold it out and get the power you need. You couldn't do that with any other solar technology because the plastic couldn't handle the temperature you would need with the inorganic semiconductors. So I need to tell you that this is a developing area of research, and back at the turn of the century, the efficiency of these solar cells was only around 3%, but as you can see, those efficiencies are rapidly climbing, and the black dots are when you have one solar cell, and the red are when you have a couple stacked. We call those tandems, and I'll say more about them later. And so now, back in December of last year, 10% efficiency was announced by Heliotech, and that was confirmed by an independent source. And then Mitsubishi over in Japan is claiming that they're beyond 10%, but this data is from NREL, and they only plot it once it gets verified by an independent laboratory. So it's really exciting when you see the trajectory that this is on, and we hope to go up to 15 and maybe even 20% over the next 5 to 10 years. One other thing I need to point out, when we talk about efficiency, we measure that under normal one-sun conditions at a 90-degree angle at 25 degrees Celsius, which is room temperature. But in the real world, early in the day, you don't have that much sunlight. The light doesn't come in at that angle. And in the middle of the day, the cells heat up. And it turns out silicon cells don't work as well at lower lighting levels, and when they heat up, their efficiency goes down. But organic solars hold their performance at lower light, and they hold their efficiency at elevated temperatures. And so if you had an organic system and a silicon system both rated at the same power, you'd get 30% more over the year from organic. And so really, to be fair, you need to multiply by 1.3, and this is equivalent to being at 13%. So the gap is not as large as it appears to be.
Is the maximum 30%?
And silicon, the record for silicon is 25%, and the modules you typically get are around 18%. Okay, now I will tell you how the organic solar cells work. So one thing I haven't explained yet is how do you get the electrons to go to one electrode and the holes to go to the other one? And the answer is you need to use two different kinds of metals. And so with organic solar cells, we often use indium tin oxide on one side, and we use that because that's the transparent conductor used in displays. If you have a laptop computer or a flat screen TV, then almost certainly you have indium tin oxide electrode on there. And so that's a readily available material, and we use that for the side where the light comes in. And then on the other side, we use a metal that loves to give away electrons, something like calcium. So ITO kind of likes to take electrons, and calcium kind of likes to give it away. And if we draw an energy diagram, ITO fills its energy levels up to where you see here, and calcium goes up much higher. And for comparison, you see the conduction band and the valence band of the semiconductor. Now, if you bring these materials into contact with each other, those energy levels will not stay there. You've got all these electrons in calcium sitting up in high energy states, and you've got empty states in ITO. And what will happen is those electrons from calcium will diffuse over, and you'll get net negative charge on the ITO side and positive charge on the calcium side. And that will keep happening until those energy levels level out. And here the diagram is just a little bit different. The lines for the metals are the top of the occupied levels, and then these lines are the conduction band and the valence band. And so eventually there will be enough negative charge over here, and those electrons will start to repel each other, and it'll sort of balance everything out, and you'll get to where the electron doesn't really care. It would be just as happy to be on the right as it would to be on the left. And if you know much about semiconductors, this is called the Fermi level, and the Fermi level is equalized throughout the structure. And so now something nice has happened. With that negative charge on the left and the positive charge on the right, there's an electric field across the device, and the energy levels are tilted. And so then if you shine light on this and you kick an electron up into the conduction band and form a hole in the valence band, that field can pull the electrons to the right, and it'll pull the holes over to the left. And so that's how we separate the positive and negative charge. Now, unfortunately, it's not quite that simple. And if we make that structure with just one semiconductor, we don't get a very good solar cell. And the problem is that the electron and hole are attracted to each other, and they form what's called an exciton. And the electric field is actually not quite strong enough to rip them apart. And so the electron and hole will hang out together, and eventually that electron will fall back down. We call that recombination, and we lose the energy. And so researchers had to figure out how to fix this problem. And Ching Tang did it when he was working at Kodak. He realized that there needed to be a second semiconductor, and this is where the donor and the acceptor come in. And so if you have a layer of donor and a layer of acceptor, light will come in, it'll be absorbed, and it will form an exciton. And then that exciton will travel or diffuse to the interface between the semiconductors. And then the electron will transfer over to the other semiconductor because the conduction band is lower in energy. And remember, electrons always want to try to get lower in energy. Now the electron and hole are not as tightly bound to each other, and then they can travel out to the respective electrodes. So at this point, we're almost there. This will almost work well. You can do about 3% efficiency with this structure. The one last thing we have to do is make sure that we capture all the excitons. Turns out they only travel about 7 nanometers, and we need to make this film about 100 or 200 nanometers thick to absorb the light, so we only capture them if they're formed near the interface. But that's easy to fix. We just need to nanostructure the materials to form what we call a bulk heterojunction. A heterojunction is a junction between two semiconductors, and bulk means we have the heterojunction everywhere in the thin film. And this is from the cover of the Materials Research Society bulletin, and you see different approaches that people were using. They would grow brushes of nanowires and fill them in with a semiconductor, or they would take a donor made of a polymer and an acceptor made of fullerene molecules and cast those films and get a blend, or they would smear down crystals of titania and then coat that with dye molecules. There are lots of different ways to make what we call a bulk heterojunction. And now, no matter where the exciton is formed, it'll be right at the interface between the donor and the acceptor, and so we can separate that. So this brings me to the research that we do right here at SLAC. To make these solar cells work well, we need to know where the donor molecules are and where the acceptor molecules are. We have to make sure that the regions of the donor are small. They can't be more than about 10 nanometers. If they're wider than that, the excitons might not make it to the interface. But we also have to make sure that the electrons have a pathway to get to the top electrode and that the holes have a pathway to get to the bottom. If there are isolated islands, then the charge carriers can't get to the electrodes. And we need to know things like, do you have pure regions of donor and pure regions of acceptor, or do the acceptor molecules mix in with the donor region? And it turns out that if the acceptor is a fullerene, which is like a soccer ball made out of carbon, they can mix with the polymers that we use as donors. The polymers usually have insulating side chains on them, and we use that to make the polymers soluble so that we can put them in solvents and print them. And if the fullerenes go in between those side chains, then you get these mixed phases, and it turns out they're only good at transporting holes, and so if that's all we have, we don't have a way to get electrons out. And so we need to have plenty of fullerenes so that we can fill in all those spaces between the side chain and still have fullerenes left over to form a pathway for the electrons. And so if the fullerenes go between the side chain, we need a lot of fullerene. We need about 75% of the film to be fullerene. On the other hand, if we use other polymers where the side chains are really close to each other, the fullerenes can't get in there, and then we'll have pure regions of polymer or donor and pure regions of acceptor. And normally we want about half the film to transport holes and half to transport electrons. And so then our optimal blend ratio is about 1:1. So by understanding how the molecules mix at the molecular level, we can understand what ratio to use, and we can figure out how to make a good solar cell. But we want to know, even more than that. We want to know precisely how those fullerene molecules touch the polymer. It turns out that those details can be really important for determining how well charge moves through the structure and whether or not the electrons and holes will recombine with each other. And so we come up here to SLAC, and we do X-ray diffraction. And so 2 miles up the road, electrons start and they get accelerated down the track, and then they come to this ring, which is in one of the buildings next door, and suddenly their direction is very suddenly changed. And when a charged particle is accelerated like that, it'll emit X-rays. And so that's how we get X-rays. And it's a very, very intense source of X-rays. We have X-rays down the hill at Stanford, but it's not powerful enough to do these experiments. So we're lucky to have one of the only synchrotrons, one of the few in the world, to be able to do this kind of experiment. So we come in with X-rays, and we diffract them off of our materials, and we get these complicated patterns, and it's a little bit hard to explain how we interpret those patterns. But suffice it to say, we can find out how the molecules are packing. We can see how far one polymer chain is from the other. And we can see that without the fullerenes, these chains are 21.5 angstroms apart. And when the fullerenes come in, they are 30 angstroms apart. We can measure that very, very precisely. And we can do even better than that. We can analyze the pattern and come up with a pretty good guess of how the polymers and fullerenes pack. And then we can send that to our collaborators at Georgia Tech, who are theorists, and they use computers to do calculations, and they find out, would the energy be a little bit lower if this side chain bent a little bit? And would the energy be lower if those rings there twisted a little bit? And they can run this many, many times and explore all the possible geometries, and they can find the one with the lowest energy, and then they can go back and calculate what the X-ray pattern should be until they get a perfect match with the actual data we see. And in that process, we can find out almost exactly where all of those molecules are sitting. And then that helps us go back to the chemists, and we're able to tell them, you know, if you would put another carbon atom over here, that would make the structure a little bit better and line everything up for us. And so that's how a large team of us are able to make these materials better. And that's why every couple of months the solar cells get better. And so here, the blue, those are the fullerenes that transport electrons. The red, that's the backbone of the polymer that transports the holes. And orange, those are the insulating side chains. And what you see, the electrons, they can go in one direction only. They can't go left or right because of the insulating side chains. They can't go up or down because of the polymer. And now you see why this material by itself won't make a good solar cell. The electrons can't get up and down. They can't get to the electrodes. And we need more fullerenes. We need a pure fullerene phase so the electron can come out and get into that phase and then go to the electrode. And we can zoom in on this, and we can look at the pure polymer, and we can look at the polymer with the fullerene. And in the pure polymer, the backbones line up on each other really nicely, and the holes can just zip along there. But when we put the fullerenes in, if you look at this closely, you will see that the polymers move up and down, and the odd ones go up so that they can interact with the fullerenes, and the even ones, they go down to interact with the lower fullerenes, and the polymers twist, and they don't pack as well on each other, and so the holes can't move through here as well as they can in just the pure polymer. And so we know that, and we just figured that out recently, and we'll go to the chemists and tell them about this problem, and they will redesign these molecules so that it'll work better, and the fullerenes will not disrupt the packing. And so that's just one example of the kinds of things that we're able to do with the tools we have here to make the materials better. So let me briefly address a couple of other key questions. Can the solar cells last for 25 years? That's a key question. People who are skeptical of this field, they see a newspaper in the sun fade. They see the colors go away, and they wonder if these materials are going to be able to last that long. So in my lab, we have a whole bunch of lamps. It makes it the best place at Stanford to go on a rainy day. It's always sunny in my lab. And we have the electronics to test about 100 solar cells. We prefer to do it indoor so that the light is always the same, the temperature is always the same, and we can repeat the experiment and get the same results every time. And we plot the efficiency over time, and we see that they degrade rapidly at first, and then it really slows down. And if we extrapolate this, the solar cells would last for about 6 years. We would lose about 20% of the performance in 6 years. And so that's not good enough, but we're optimistic that we will figure out why the cells are degrading, and we will figure out how to make them last for 20 to 30 years. And I'll tell you what I think we'll need to do. We will definitely need to encapsulate them. We'll need to protect them from air. These materials are much more stable when you keep air away from them. We will probably need a UV filter, maybe some glass with titanium on it, because UV photons have a lot of energy. That's why they damage your skin, and they can break these molecules also. So the filter will help a lot. We won't be able to use just any molecule. We'll need to use stable ones like the ones that are used in car paint. And then here's why I'm optimistic. When I was a graduate student, I didn't work on solar cells back then. I worked on organic light-emitting diodes, and they didn't last very long back then. But when we passed this on from the university to companies, and they put large teams of people on it, they figured out how to make those diodes very stable. And if you have a Samsung cell phone, you probably have an organic light-emitting diode display in there. Samsung right now has invested $2.5 billion to build a factory to make TVs with this technology, and they believe that in about 5 years, OLED displays will replace liquid crystal displays. And we will be able to learn from that industry and do everything they did to make those displays stable, to make solar cells stable. And then the last research topic, we have to print everything if we want to make really low-cost solar cells on these cheap plastic substrates. And that means we can't use indium tin oxide because that is sputtered, and they do it at high temperature, and it's not as flexible as we would like. So Peter Poymans and others at Stanford have figured out how to spray down silver nanowires, and silver is a wonderful conductor, and by only having it in certain places, it can remain transparent. And when we make solar cells with silver nanowires and ITO, we get exactly the same performance. You can't tell the difference. And so that problem has been solved as well. And then there is, I forgot, one last topic. So how could we do even better than 31% efficiency? Well, the answer is you need to stack more than one solar cell. You need to make what's called a multi-junction cell or a tandem solar cell. And this has already been done. And the strategy is you use a high band gap first, and you absorb the high energy photons. And with that cell, you can generate a high voltage. The lower energy photons, they'll go right through it. And then you can have a cell with a medium band gap, and you can generate a medium voltage with that. And then the lowest energy photons can be absorbed in a third solar cell. And then you can just connect these in series, and the voltages will add, And now you can do much better than if you just have one solar cell. And this is what was done to get the world record, which is 43% efficiency. There is a problem. It costs $50,000 per meter squared to do this. You can see that there's over 20 layers, and it's not just that there's a lot of layers. This is all one crystal, and they carefully grew this so that each crystalline layer grew off of the other layers. They need to have the high quality to prevent the electrons and holes from getting trapped and recombining. Now, that doesn't mean that this is out of the game. You can have concentrators, and you can focus the light on a very small multi-junction cell. And so there are some people who believe that this technology will be the winner. I think they're in the minority these days, but there are people who believe that this is going to be the way to go. Now, in organics, we can do this also, but we have a huge advantage. Our materials don't need to be crystalline, and we don't have to lattice match the crystals on each other, or we don't even need to have crystals. We can just grow one cell and then grow another one. In fact, we can even just grow our cells on top of silicon or SIGs and just make them more efficient. And we're just spraying these materials down. We can do that at very low cost. And so we have a low-cost way of making multi-junction solar cells. Right now, a startup company in Germany called Heliotech has already obtained 10% efficiency, and we think we can do way better than that. So to wrap up, the solar industry is growing very fast, 40% per year. Grid parity has already been reached in many places, and it will be reached almost everywhere by 2020. There's a fascinating race between silicon, cadmium telluride, SIGs, amorphous silicon, which I didn't even say much about, multi-junction cells with concentrators, and organics, and even a few others that are still at the research stage. It's early. Silicon has the lead, but I believe any of these technologies still have a chance of being the winner 10, 15, 20 years from now. I think printing solar cells has huge potential. It's going to be critical to make the tandems to compete with the technologies that are already out there. And then finally, I hope you got a taste of the kind of science that we do at Stanford and at SLAC. And today I just talked about solar, but there are many, many other interesting areas of science for wind turbines and batteries and fuel cells. And it's a great time for connecting science with renewable energy. If you want to learn more about this, I'm the director of the Center for Advanced Molecular Photovoltaics, and we have a website. The executive director, Alan Sellinger, is back there, and afterwards he is supposed to wear one of these hard hats so that you'll be able to see him and you can ask him questions. And he's a chemist, so if you have questions about how the molecules are made, you should go to Alan to ask your questions. And I want to thank my students who helped me to develop these ideas and to gather them. I certainly don't want to imply that everything I showed tonight came from my group, but my students helped me to gather all of this information and make these slides. And I want to thank you all for coming, and I'd be happy to answer your questions.
So we can take some questions, and if you just wait for the microphone to come to you. Let's take the first one over here.
So how does the amorphous silicon compare as a thin film technology to these organics that you describe?
Amorphous silicon has an efficiency around 11%. They can make tandems also and make that a little bit higher, I think 13 or 14%. Interest is tapering off a little bit because that efficiency is stagnant. It's not shooting up the way organics are. It can only be deposited at about 1 angstrom per second, which is really slow. And if you use a roll-to-roll coater, the tool needs to be well over 100 meters long. And then that tool ends up being very expensive. So the interest, I would say, has been declining a little bit in recent years for amorphous silicon.
I know this is not exactly your area of expertise, but the slide you put up, or not really what you're talking about, but the slide you put up about the 40% growth and the bar chart showing we did 23 megawatts in the last year.
Mm-hmm.
The bar, or the section of the bar for China and Taiwan was way larger than any of the other sections, if I was reading it right. And I wonder if you have any insights as to why that would be.
I do know quite a lot about that subject, and the founder of Suntech, Zhengrong Shi, came to Stanford and spoke recently. And if you go to the Energy Seminar website at Stanford, you can view his lecture. And basically, China has invested very, very heavily in this industry. The government has provided $42 billion in loans over the last couple of years. They are realizing enormous economies of scale. They build basically what are called solar cities. They'll have huge factories where they make the silicon, and then right next door to that, they'll have huge factories where they make the wafers, and then right next to that, they'll have huge factories where they turn the wafers into solar cells, and then right next to that, they'll have factories where they make the glass for packaging the modules, and then they'll have factories to make the modules as well. It's not as much from cheap labor as you would think. That's actually a relatively small component because it's actually a pretty automated process. Part of it also, the Chinese, they were very practical and they made short-term bets. They went with technologies that were already available. Of course, they didn't invent any of it. It was all invented here, Europe and Australia, and they just manufactured it. Here, we didn't really pump a lot of effort into silicon. For the most part, we looked at second generation or third generation technology. So we've placed our bets that we can do something better than silicon. And only time will tell who's going to win that bet.
Could you go back to your grid parity slide with the countries? That one, right. In the calculations that go into this, what externalities were ignored? And a related question, how well do solar cells work in the polluted air of China?
Well, these, I should say that this is a very complicated subject, and whenever you have to describe it in 3 minutes, it's difficult. And of course, I show 1 point for an entire country, and the prices vary all over the country. The amount of sunshine varies all over the country. So people who would say that this is oversimplified, the biggest thing they would object to is that these prices, this is what residential users would pay. This is not what a utility company would pay. So this is, you're at home and you're deciding, am I going to buy electricity from the utility company or am I going to generate it myself? So the prices would be lower if you were looking in the utility sector. Specifically, the complication that you mentioned would be that there are some places in China where the air is very dirty. Well, the air wouldn't be dirty if they were using solar cells.
I have 3 questions. First one would be more probably in your direct
How about one?
field. Excuse me?
How about the first one?
Okay, yes. The first one is there's been some stuff in the news, research news lately, that there's a lot of energy in the infrared spectrum of the sun that's not being captured, and there's been some solar cell work in capturing that as well, and they say there's a lot of energy in that. Is there any possibility that that could be incorporated in printing technology for solar cells?
So when you're using a silicon solar cell, you absorb above 1.1 electron volts, or if you prefer wavelength, you absorb out to around 1,000 nanometers. And you lose the energy, the photons with energy less than that. And yeah, there's definitely some power down there. And you certainly want to get that 0.7 to 1.1 EV range. But when you go below 0.7, there's just not much to be had. And the reason is that when you absorb a photon, and it's, say, a 1 EV photon, you usually don't get 1 volt. At best, you'll get 0.6, 0.7 volts. So when you absorb 0.7 EV photons, you might get like 0.3 volts, and there's just not a lot of power there. So it's important, but it's not the whole game. And certainly when they got that 43.5, that's how they did it. They moved down to 0.7. Organics are actually not great, or we have not yet figured out how to go down to those low band gap regions. And I'm interested in putting the organics on top of silicon, because silicon's actually really, really good. And then you always run into these trade-offs of performance versus cost, and both are really important, and you have to make sure you don't drive the costs up too much when you go chasing after those low energy photons.
Let's do 2 more questions. There's one here and a fellow up there. And then we'll end the formal part of this. You guys can come down and ask more questions if you want.
You mentioned that the effective lifetime of the organic cells is about maybe 6 years at the most. Why not just make lots of cheap cells that don't last that long, and then replace them frequently? I mean, that's how the auto industry works, through planned obsolescence. That's how the computer industry works, even at a greater scale. By having computers that work just well enough for long enough, and then they're replaced quickly.
So
is that a cost-effective way to go about it?
When many of us here in Silicon Valley made the transition from working on computers and electronics and photonics over to energy, we had to learn a very hard lesson. In computers, they're constantly getting so much better than was out there before that people will throw away their old computers and phones and switch to new ones. The thing about solar is if I can't give you electrons for cheaper than the coal-fired power plant can, then you don't care. You don't want my solar cells, because they don't give you anything that you don't have. All we're doing is providing electricity, and you already have that. And so, like when cell phones came out, they'd be $5,000, and there were people who would pay that. But people aren't going to pay large amounts for these solar cells, so you really, really have to be economically competitive. And when you run the numbers, you will find that if you're throwing your cells away every 5 years and then paying someone to come out and get up on the roof and install them, you can't win. And while our semiconductor layers, we can actually put those down really, really cheap, you'd be surprised at how much just a sheet of glass costs or how much just the plastic costs. It's not saran wrap. It's a nice, smooth plastic that's really good at keeping the air and water out. And yeah, when you run all the numbers, you find that these things need to live 20, 25 years in order for it all to work out.
Just a quick comment. Us in the East Bay who have teenagers and lots of computers, we're well above 0.4. We're now at 0.48. So
You're paying 48 cents per kilowatt
so
hour.
your grid, if you update again, I know you just upgraded, but if you update again, it's going to make your argument even more valid.
Yeah,
what is the efficiency barrier? Is it simply absorption material of the whole electron pair? Why can't, depending on what your system is or your material system is, what is the physics efficiency barrier?
Well, this is the essence right here of why there is a theoretical limit. With one semiconductor, you can't do better than 31%. And that's, if you try to use a low band gap so that you absorb most of the spectrum, you end up with a very low voltage. And if you go with a high band gap so that you get a high voltage, then you don't absorb many photons and you get a low current. And electrical power is current times voltage. And so basically that's the essence of it. And that says 31% is all you can do. And silicon, they've already got 25%. And there's some detailed reasons why it's hard for them to eke out that last little bit. Part of it is silicon does not have the ideal band gap. It's 1.1 EV, and the ideal is 1.4. But that's the only huge problem. That's where you're losing 69% of the power, and then the other sources, it's just like you'll lose a couple percent because you have metal electrodes on here, and the light can't get through the metal electrode. A little bit of the light will reflect off the solar cell, and you lose little things. But this is the big one. Now in organic solar cells, we still have problems we haven't fixed yet. Our energy levels are not yet where they should be, and we don't capture all of our electrons and holes. Some of them recombine, and I was telling you how we're trying to get the molecules to pack the right way so that we can separate all of the electrons and holes and get them out to the electrodes. And that just takes time.
Okay, well, we thank you very much.
Welcome.